Here we will discuss about a method to find eigenvalues and eigenvectors of matrices. So, we will discuss about this method to find eigenvalues and eigenvectors of matrices. Recall that if lambda is an eigenvalue of a matrix A of size n by n, then there exists a vector x in the field in this vector space Fn such that Ax is equal to lambda x. Here x is not the 0 vector, or we can write this as A minus lambda times I x is equal to 0, where I is at the n by n identity matrix. So, we have the following observations, that first observation is like this: if there is a non-zero solution of, if there exists a non-zero vector x such that A minus lambda I x is equal to 0, then rank of this A minus lambda I is less than n, that this number of variables. So, in other words, that is A minus lambda I is not invertible, and that is same as, which is same as determinant of A minus lambda I is equal to 0. So, from this equation we find all eigenvalues of the matrix A. So, this equation here, the equation A minus lambda I is equal to 0. So, the determinant of A minus lambda I is equal to 0 is called the characteristic equation of A, and this is this determinant of A minus lambda I is a polynomial in lambda of degree n. This is a degree n polynomial. So, this equation is therefore, this determinant of A minus lambda I equal to 0 has at most n distinct solutions or roots and distinct roots, or with counting multiplicity this has n number of roots with counting multiplicity. And the roots of this equation, are the eigenvalues of A. So, given any matrix A, therefore, we form the matrix A minus lambda I first and then take its determinant and equate to 0 and get all roots of this equation. The roots of this equation are exactly the eigenvalues of the matrix A. Eigenvalues are also called characteristic roots sometime because of this second. So, eigenvalues of A are sometime called characteristic roots. Eigenvalues of A are sometimes called characteristic roots. Then next we will see how to find eigenvectors corresponding to an eigenvalue of the matrix A. If lambda 0 is an eigenvalue of A, then all non-zero solutions of the system A minus lambda 0 I x is equal to 0 are the eigenvectors corresponding to the eigenvalue lambda 0. So, next let us see one example where we find eigenvalues and eigenvectors of matrices. So, find all eigenvalues and corresponding eigenvectors of the matrix A, that is given by 5 4 2 4 5 2 2 2 2. So, we solve like this. Solution: first we find characteristic polynomial of A. The characteristic polynomial of A is determinant of A minus lambda I. Here we consider I be 3 by 3 identity matrix. So, the given matrix, this A minus lambda I is therefore 5 minus lambda, 4, 2, 4, 5 minus lambda, 2, 2, 2, 2 minus lambda, and we have to find out its determinant of this matrix, and that is one gets like this. After computation, one can find the determinant be like this, minus lambda minus 10 into lambda minus 1 whole square. So, the roots of this equation determinant of a minus lambda I are this: lambda 1 is 10 and lambda 2. So, now the eigenvalues are lambda 1 equal to 10, lambda 2 is equal to 1 with multiplicity 2, where multiplicity of lambda 2 is 2. So, next we shall find out eigenvectors corresponding to these eigenvalues. So, eigenvectors corresponding to lambda 1, that is equal to 10. So, we find like this. Here we have to solve the system, we have to solve this homogeneous system a minus 10I into this x is equal to 0, where x is this x1, x2, x3. This has 3 components. This is a vector in R3 we can take. So, that is the system is like this: a minus 10I is like this, minus 5, 4, 2, 4 minus 5, 2, 2, 2 minus 8, and this x1, x2, x3. So, this system is like this, this is equal to 0. Now, we consider echelon form of the coefficient matrix to find all solutions. So, the echelon form of the coefficient matrix will be like this. Here this coefficient matrix is minus 5, 4, 2, 4 minus 5, 2, 2, 2, 8. And an echelon form of this is like this: minus 5, 4, 2, 0, minus 9, 18, 0, 0. So, the system of equation is now the system is minus 5x1 plus 4x2 plus 2x3 is equal to 0, minus 9x2 plus 18x3 is equal to 0. Here we consider x3 as the free variable, x3 is the free variable, that is a variable which is free to take any value in the field. So, let x3 is equal to alpha, alpha belongs to R, then we get x2 is equal to twice alpha and x1 is also equal to, that is x2, and it is equal to twice alpha. So, the set of all eigenvectors corresponding to lambda 1 is equal to 10 is this set, that is consist of twice alpha, alpha, alpha belongs to R and alpha is not equal to 0. If alpha equal to 0, then we get this vector be 0 vector, and 0 vector cannot be an eigenvector. So, this is the set of all eigenvectors corresponding to the eigenvalue lambda 1 is equal to 10. So, next we will find this eigenvector corresponding to lambda 2, eigenvectors corresponding to lambda 2, that is equal to 1. So, here we have to solve the system A minus I times x is equal to 0, or it is 4 4 2 4 4 2 2 2 1 x1 x2 x3, that is equal to 0. Again we get the echelon form of the coefficient matrix be like this. Echelon form of the coefficient matrix is given by 4 4 2 0 0 0 0 0 0. So, this system will be, this system is given by 4 x 1 plus 4 x 2 plus 2 x 3 is equal to 0, or 2 x 1 plus 2 x 2 plus x 3 is equal to 0. So, here we are having only one equation and 3 variables. So, 2 variables are free variables and x 2 and x 3 are therefore free variables here. X 2 and x 3 are free variables. So, let us take that x 2 is equal to alpha and x3 is equal to x3 is equal to beta, where alpha and beta they come from this set of real numbers, because we are considering a real system over real numbers. So, then we get x1 be like this, that is minus half into twice alpha plus beta. So, now the set of all eigenvectors corresponding to the eigenvalue lambda 2 is equal to 1 is given by this minus half into twice alpha plus beta alpha beta, where alpha beta belongs to the set of real numbers and alpha and beta do not take the 0 value simultaneously. Alpha and beta do not take the 0 value simultaneously. Otherwise, this vector will be a 0 vector and that cannot be an eigenvector. So, this is how we find eigenvalues and eigenvectors of matrices. So, next we shall discuss about another important concept, that is diagonalization of matrices. Diagonalization of matrices. Here also we consider only square matrices. That let us see first what is the meaning of diagonalization of matrices, that we give in this definition. A square matrix A of size n is said to be diagonalizable if there exists an invertible matrix P of size n by n, such that P inverse A P is a diagonal matrix. In other words, this A is similar to a diagonal matrix. In other words, A is similar to a diagonal matrix. So, not all square matrices are diagonal matrices, that is not for any square matrix A we get an invertible matrix P, so that we will have this P inverse A P will be similar, this will be a diagonal matrix. So, here we shall see two more definitions or terminologies for discussion of this diagonalization of matrices. So, let us see that definition of multiplicity, geometric multiplicity and algebraic multiplicity of an eigenvalue. So, let lambda 0 be an eigenvalue of a matrix A of size n by n. Then the geometric multiplicity, of lambda 0 is the dimension of the eigenspace of lambda 0, that is the dimension of the solution space of this homogeneous system A minus lambda 0 I x equal to 0. Here also we define algebraic multiplicity of lambda 0, that is the algebraic multiplicity of lambda 0 is the largest positive integer k, such that lambda minus lambda 0 whole to the power k is a factor of this characteristic polynomial, that A minus lambda I. Characteristic polynomial of this A minus lambda I, or in other words, this is the multiplicity, lambda 0 is the multiplicity of, this algebraic multiplicity of lambda 0 is actually multiplicity of lambda 0 as a root of this characteristic equation. So, next we will just state some known results on this geometric multiplicity and algebraic multiplicities, known results, and also that relation among eigenvectors corresponding to different eigenvalues. So, the first one is like this: the algebraic multiplicity is greater than or equal to the geometric multiplicity of an eigenvalue, that the algebraic multiplicity of lambda 0 is not less than the geometric multiplicity of lambda 0. Then next we have another important result that we shall use, is that if lambda 1 and lambda 2 are two distinct eigenvalues of A, and x1 and x2 are eigenvectors corresponding to them of course respectively, then x1 and x2 are linearly independent. That is, eigenvectors corresponding to distinct eigenvalues are linearly independent. One can prove this easily. So, next we shall use these results and find this diagonalization of matrices. Of course, we are having an important criteria which tells about diagonalization of matrices, and here is this result that tells a necessary and sufficient condition for diagonalization of matrices. So, let this A be a matrix of size n by n, be a square matrix, with eigenvalues lambda 1, lambda 2, lambda k. Let gamma I be the geometric multiplicity of lambda I from 1 to k. Then A is diagonalizable if and only if this gamma 1 plus gamma 2 plus gamma k is equal to n, that is the size of this matrix. Or in other words, we can also relate this a matrix is diagonalizable if and only if this algebraic multiplicity is equal to the geometric multiplicity of every eigenvalue. So, here we are having a corollary that one gets if this matrix of size n by n has n distinct eigenvalues, then A is diagonalizable, because the geometric multiplicity of an eigenvalue is at least 1. So, then next we will see a method for diagonalization of matrices, or that we write as an algorithm to diagonalize a matrix. So, here our input is a square matrix A of size n, Then first step is this, we find eigenvalues of A, find eigenvalues of A, say lambda 1, lambda 2, lambda k. Here k is less than or equal to n, of course. Then second step is we find geometric multiplicity of is lambda I from 1 to k. Let the geometric multiplicity of lambda I be gamma I from 1 to k. Then third step is that we check whether the sum of the geometric multiplicities, that if gamma 1 plus gamma 2 up to gamma k plus gamma k is equal to n, then we continue this, and then continue, otherwise we return that A is not diagonalizable. So, in fourth step we know the geometric multiplicity of each eigenvalue and sum of the geometric multiplicities equal to n. Then here for each eigenvalue we shall find a basis for the eigenspace. So, here find a basis for the eigenspace Si corresponding to the eigenvalue lambda I for I 1 2 up to k. So, let the basis be, let this x j lambda I such that j is equal to 1 2 to gamma I be a basis for Si. So, dimension of Si is gamma I. So, therefore, in this set we have this gamma I number of vectors, and this is a basis for this eigenspace corresponding to the eigenvalue lambda I. So, here this I is therefore from 1 2 to k. For each lambda I we consider a basis for its eigenspace Si. So, now in this step we find that invertible matrix P be like this. Take P be the matrix that it is consist of x1 lambda 1 up to this x gamma 1 lambda 1, then x1 lambda 2 x gamma 2 lambda 2, like this x1 lambda k up to this x gamma k lambda k. That is, this is a matrix of size n by n, where is x j lambda I is a column vector or a matrix of size n by 1. Therefore, P is a square matrix of size n by n. Notice that this P is invertible matrix because all these columns in P are linearly independent, and hence this rank of this P is equal to n, and therefore, it is invertible. So, now we get that this P inverse A P is equal to the matrix where in this diagonal first this gamma 1 in number, they will be gamma 1 in number or lambda 1, then lambda 2, like this lambda k, they are gamma k in number, and the rest are the 0 matrices. So, this is how we find that diagonalization of this matrix A. Let us see this example to support this algorithm. Let us have this example. Here we consider the same matrix of the previous example. Here consider the same matrix of the previous example, that is, A is this matrix 5 4 2 4 5 2 2 2 2, and also recall that this is 2 eigenvalues. Recall that A has 2 eigenvalues, lambda 1 is equal to 10 and lambda 2 is equal to 1, where lambda multiplicity of lambda 2 is 2, or in other words, algebraic multiplicity of lambda 2 is 2. In other words, algebraic multiplicity of lambda 1 is 1 and that of lambda 2 is 2. So, then next we shall find geometric multiplicity of lambda 1 and lambda 2. So, again recall that the eigenspace of lambda 1 is this set S1, that is consist of twice alpha alpha such that alpha belongs to R. So, here we are including the 0 vector. So, therefore, we do not have to take alpha is non-zero. So, notice that dimension of that is gamma 1 is dimension of S1, that is equal to 1. This also we get again from that rank nullity theorem. So, next we consider the eigenspace of lambda 2. So, the eigenspace of lambda 2 is the set S2. It is consist of minus half into twice alpha plus beta alpha beta. Here alpha beta are real numbers. Here alpha beta are real numbers and the dimension of S2, that is geometric multiplicity of lambda 2. Gamma 2 is dimension of S2, that is equal to 2. Now, this gamma 1 plus gamma 2, that is equal to 3, that is size of matrix A, size of the matrix A. So, this matrix A is diagonalizable. So, next we shall find that invertible matrix P. So, for that we have to find a basis for S1. So, a basis for S1 is its dimension is 1. So, we can take any non-zero vector in S1 and that will be a basis for S1. Then a basis for S2 is that its dimension is 2. So, therefore, it is consist of two linearly independent vectors minus 1 1 0 and minus half 0 1 that we have obtained by taking that has been obtained by taking alpha equal to 1, beta equal to 0 and then alpha equal to 0, beta equal to 1. So, now this matrix P will be like this. We take the bases in S1 and S2 as columns of this matrix P. So, therefore, first column will be basis for S1, that 2 to 1, and then we write basis of S2. So, that is minus 1, 1, 0, minus half, 0, 1. So, now one can check that this one checks that this P inverse A, P is the matrix, is the diagonal matrix 10, 0, 0, 0, 1, 0, 0, 0, 1. This is how we find this matrix P to diagonalize the given matrix A. Next, we will see one example that not all matrices are diagonalizable. Not all square matrices are diagonalizable. So, let us see one example of it, that here we consider the matrix A be like this, that minus 3, 1, minus 1, minus 7, 5, minus 1, minus 6, 6, minus 2. So, here one checks that the eigenvalues be like this. Eigenvalues of A are lambda 1 is equal to minus 2, lambda 2 is equal to 4, and lambda 1 is a multiplicity, lambda 1 is a multiplicity 2. So, eigenspace of lambda 1 is the solution space of, here eigenspace of lambda 1 is the solution space of the system A plus twice I x equal to 0. Here this rank of, one can check that this rank of A plus 2 I is equal to 2. So, one checks that rank of A plus twice I is equal to 2. So, geometric multiplicity of lambda 1 is 1. Similarly, we get the geometric multiplicity of lambda 2 is also 1. Therefore, so here gamma 1 plus gamma 2 is equal to 2, and that is not equal to 3. So, in this case A is not diagonalizable matrix, not a diagonalizable matrix, and that's all. This lecture will stop here, and this diagonalization of matrices, they are also useful, and in the next lecture we shall discuss that using diagonalizable matrices we can also compute higher power of matrices. That's all for this lecture. Thank you.